going on, everyone? Today I want to summarize a central result of a field that I do research in. The result itself, I guess the intuitive build-up to it is certainly very important, but the result itself is actually quite a simple mathematical derivation. It's a bound. We're going to use things like the Cauchy-Schwarz inequality, and we're going to do some, basic quantum mechanics. Okay, so what do we want to do here? Let's set the stage. A question that you might want to ask is the following. Let's say I give you some Hamiltonian, and I'm going to call it h hat, and let's say I give you a complete set of energy eigenvectors, complete with its energy eigenvalues. Then one thing that you might want to ask is, how do these systems go to equilibrium? Can I describe something that looks like equilibrium? So especially when your initial state is a pure state. So we are in an extremely sort of quantum setting. H hat is going to be the thing that generates our dynamics. So we're going to pick some pure state psi, which will be a function of time, and we're going to assume that this energy spectrum is discrete. It could be infinite. So we have the ground state energy E0, we have then the first excited state, and the second, and so on. This could potentially stop at some finite number, like for a spin system, or it could go on forever. In fact, it doesn't really change our discussion too much. But basically, I've sort of cut myself off here. Basically, this pure state psi then would be time evolved with the following standard equation. So you have your complex amplitudes, Cm, and then you would have how they rotate in time. So we're going to write this in the energy eigenbasis. So we get a negative here, Emt, and then we have the energy eigenvector Em here. So Cm, as always, is going to be the following quantity. So it's the projection of your pure state psi onto the energy eigenvector Em here. And of course, in this equation, and as usual on this channel, what I'm doing is I'm setting h bar is equal to 1 just to make our notation and how many symbols we have to carry around a little bit easier. Okay, so one thing that I want you to notice here is that, I know this is kind of awkward notation, but this is equal to this equation here. One thing I want you to notice is that this equation itself won't go to equilibrium. And the reason for that is that this is just, you can just think of this as a vector. A vector where its entries, where, for example, the first entry would be c of 0, e to the, like that. So we could think of it in this way. The next one would be c1 e I e1t, if we wanted to write it this way, in the energy eigenbasis. And basically what's happening here is that we just have a bunch of entries that are rotating around in the complex plane. And so that's just going to go on forever. That's never going to go to equilibrium. We're not going to find equilibrium this way. These are periodic functions. Of course, there's more entries here. This would be much bigger than what I wrote, but yeah. And so before I forget to say it, the reason why we don't care about if we have an infinite number of energies or not, and why we can basically just go and assume we have a discrete spectrum, is because what we're going to assume is that we're going to assume we have a finite energy density, so that basically what we can do is we can approximate, if we say E0 is less than or equal to E1 is less than or equal to E2, and so on, then we can approximate this m is equal to 0 up to n, and then all of a sudden this is something that is, arbitrarily close to our actual state. And we can always do this for the types of states that we're going to be interested in. Otherwise, those states would have infinite energy. They just wouldn't have properties that we'd be interested in. Okay, so we can't describe equilibrium with the state itself. So what can we describe it for? Well, what we could describe it for is what we actually measure in experiment, and that is an observable. So we could take some observable A here, and what I'm going to do for this observable A is I'm going to write the following notation so that we can use it. So if I'm going to write it in the basis of the energy eigenstates, and I'm always going to refer to this as AMN as a short form notation to get us through the derivation. So time evolving this observable would be like the following. We get psi of t, a psi of t, it's a bad t there, but that is a t in fact, is equal to some mn of cm cn amn e to the power of em minus en. Sorry, I'm squeezing things here like that. But basically what you'll notice about this function now is that, you know, maybe it'll do something like this. So if I call this a of t here, and t, maybe we have this, and maybe this line here is the equilibrium value. You might get some function that looks like this, and it could actually settle down to an equilibrium value. The problem is that because there is a finite number of terms here, it's still a periodic function, or I believe the correct term is an almost periodic function. So it won't quite relax. It won't fully relax until we reach the thermodynamic limit. But what we want to do is we want to study finite size effects along with studying the process of going to equilibrium. Okay, so we're studying something called quantum equilibration here. And so if it does indeed go down and maybe sit at equilibrium, we'll sit at equilibrium for, you know, an arbitrarily long time, so that we can say the following instead. Our observable does go and sit at equilibrium. That equilibrium would have to be given by the infinite time average of the dynamics. So to write that, what that would be is that the equilibrium value, which I will sort of lazily write as a of infinity, is equal to the limit as big T goes to infinity of 1 over t integral 0 to big T. We'll just write this for now. A of t, the expectation value of t in time, dt. So let's write that out in completion, expand out what we mean by all of this. So limit as t, big T goes to infinity, 1 over t, 0 t, and then we're going to get sum of m and n is equal to 0. These will go up to big N, so this is just this finite energy condition that we're going to talk about, or that we're going to use. And this is Cm, Cn, Amn, e to the I, Em minus En, t. Okay, so what terms are going to survive this infinite time average? And basically what they'll be is it's going to be terms where Em minus En is equal to 0. And the reason for this is that if this is true, then this term no longer oscillates. It no longer rotates around in the complex plane. It will be a value that is constant in time, so its time average is itself. And all of the terms that are going to get canceled by the infinite time average are going to be terms where this isn't true. And the reason why that's going to happen is because they're going to rotate around in the complex plane, and they're just going to circle around, the unit circle, and that's just going to give 0. The average of rotating around the unit circle is 0, right? So it's going to give a 0 contribution. So what energies are going to give us this? Well, one thing that you can do is you can say, let's do quantum chaotic systems. Let's study this for quantum chaotic systems. And then what you would expect is that the only condition where you expect this to happen would actually be, there's some subtle details here, but what this would actually be is that the index m would have to be equal to the index n. And that's due to something called level repulsion. It's something I'll talk about more deeply in a future video, but for now, this is something that we can safely assume, if we've treated our problem correctly, that a quantum chaotic Hamiltonian, it's very, very probable that this here, em minus en is equal to 0, then implies that m is equal to n. So then putting all of that together, that means that a of infinity, again, lazy notation, I'm not actually taking the limit as t goes to infinity, I'm taking the infinite time average. This is just then equal to cm squared amm. M goes from 0 to n. Okay? So interestingly here, we can actually extract a mixed state from this. And in particular, that mixed state is something that I'm going to call omega. Omega is called the diagonal ensemble, and it has diagonal entries like the following. Okay, so then what we would have is that a of infinity, that's a really bad infinity, what we would have is that a of infinity is equal to trace of omega times a. And so this is general in the sense that if an observable does go to an equilibrium, it experiences equilibration, its equilibrium expectation value will be given by this equation here. Okay, but this doesn't actually tell us that we've gone to equilibrium, right? What we would really want to describe is some type of average distance to equilibrium, right? So we could define the following quantity that I'm going to call sigma a squared, because it's kind of like a variance. This is going to be defined as being the limit as t goes to infinity, 1 over t, integral 0 to t, and then we're going to have the square of the expectation value of a in time minus a of infinity, so the equilibrium value, squared dt. So what you should gather from this, very poorly written equation in terms of my handwriting skills, is that what we're doing is we're asking what is the average distance to equilibrium if we average over all of time. So you can consider this a distance to equilibrium. And basically what we're going to find is that this actually really depends on something called the purity of the diagonal ensemble. So trace of omega squared is really going to determine how small this quantity is. And we'll talk about why that's interesting and the interpretations of this. But let's actually derive a bound. The result that we're interested in proving here is a bound on this quantity here. You can find this bound in a number of papers, but I'll link to one in the description for an example. But yeah, this is a relatively famous result, a very central result to my field, but I feel like it's actually quite easy to understand and follow. Okay, so let's actually just expand out what this means. You can check that I did this correctly yourself. But what we get is we're going to get the limit as t goes to infinity of 1 over t, integral from 0 to t, and we're going to get a sum where I'm going to say m does not equal to n, and k does not equal to l. And all of these will go from 0 to capital N. And why I've done this will make sense once I've written out all of the equations. Cn, Cm conjugate here. And then we have Ck, Cl conjugate. And we're going to have, running out of space already, Cm, N, A, L, K. And I'm going to write the time evolution down here, but it's multiplied down here by a big time term. And that's going to be Em minus En plus El minus Ek times t here. And all of this is, there's going to be a dt, so I'm just going to slide that in down here. So basically we're going to want to do the same thing as we did last time. But before we do that, let's discuss a few things about this equation. So basically what I did there was I took the exact same equation. I just filled in the definition of A of t, and I filled in the definition of A of infinity here. And basically all that does is when you subtract A of infinity off under our assumptions, is it just deletes the diagonal term. So it deletes the terms from your expression where m is equal to n, and then I also multiplied it by its complex conjugate because we have this square here, and this gives us the same thing for k and l that comes from the other term. You put all of these things together, you should get this equation. Okay, so which terms now are going to survive the infinite time average? Well, again, it's going to be when Em minus En plus El minus Ek is equal to 0. And we already have the conditions that m cannot be equal to n, and we have the conditions that L cannot be equal to K. Now we're going to put another strong assumption on our spectrum, and that spectral property is going to say the following. What we're going to say is that, again, the only solutions will be given by matching indices to this equation. And basically ignoring this condition, what we're going to say is that the only way that this condition could hold is if m was equal to n and L was equal to K. And another condition that could make this work is that L was equal to N and M was equal to K. So we're basically matching the indices from the positive terms to a negative term. And what this is called is it's called the no resonance condition. It's used as a mathematical trick to help you proceed in problems. You don't expect this condition to be violated for chaotic systems, at least not in a very large way. Okay, so with this knowledge then, which pair can we choose? Well, we can't choose this one because it violates our sum condition. And of course we can't pick that because it violates our sum condition. So what we're left with is this. And those are all of the indices and the rules for the indices that are going to survive the infinite time average, basically. And so when I then plug in that rule, the surviving expression is the following. So sigma A squared is equal to the sum of m does not equal to n. And then we have the probabilities here, Cn squared, Cm squared. And I'm going to keep these two things separate, even though we could simplify this as well. A and M. So this is almost a really nice equation to work with, but actually we're going to do something to simplify it a little bit to start our bounding process. Our end goal is to show that this is really small, that we do in fact spend a lot of time near equilibrium. In fact, the variance about equilibrium goes to 0 in the thermodynamic limit. And to do that, we're going to introduce our the following. This here can be rewritten as equal to, writing out the full sum without the condition. So m and n can be anything. We don't have this condition anymore. And then we have cn squared, cm squared, amn, anm. And then now we're just going to subtract off the term that we didn't want in this sum. So we just sum over all of the diagonal terms. So we have m cm to the 4. We have amm squared. So clearly what's going to happen is that this whole thing is going to be bigger than if I just didn't have this portion of the equation, right? So we can get our first inequality here and say that this is less than or equal to sum cn squared, sorry, this is over m and n, cm squared am n a n m. Okay. So the reason why I wanted to leave it in this form was so that if you're following along, it might become obvious that this equation is actually equal to the trace of a times omega, remembering that this is just the diagonal entries of omega, times a times omega, right? So we could see that the CNs might be responsible for this omega, and this could be responsible for the other omega. So the next thing we're going to want to do is we're going to want to bound this even further. And to do that, what we could do is we could appeal to the Cauchy-Schwarz inequality for matrices specifically. So if I have the trace of p dagger times q, then this is going to be less than or equal to the square root of the trace of p dagger times the trace of q dagger. So letting this be p and let this be q, then our whole expression is less than or equal to the square root of trace a squared times omega squared, all to the power of 2, which is then just the trace of a squared omega squared. Now, because both of these are called positive operators or positive matrices, now all of their eigenvalues are going to be greater than or equal to 0, specifically because of the square here and the fact that they are Hermitian. What's going to happen is we can use something called like an operator inequality, and the inequality is the following. If I have the trace of p times q again, this is less than or equal to, and this is if they're positive semi-definite, it's equal to the largest singular value of p times the trace of q. And so all of this is going to come together to tell us that sigma a squared is less than or equal to the largest singular value of a to the power of 2 times trace of omega squared. Okay, so this is just a number. We could pick an observable that has this number being independent of system size if we want to. So the actual quantity of interest is the following. So let me give myself some room here to put a plot, but basically what you should notice in this plot that I'm going to put up is that trace of omega squared goes to 0 exponentially fast. So if you had perhaps a spin 1/2 system, you would expect that the trace of omega squared would go to 0 like 2 to the minus L, where L is the number of spins you have on your lattice. And so as we approach the thermodynamic limit for well-behaved states, we expect them to concentrate very strongly around their equilibrium value in late times. Say well-behaved states, what I mean is, what is this equation, right? Trace of omega squared is equal to, well, it's the purity of the diagonal ensemble, and that is the sum of the CMs to the power of 4. And what we basically can intuitively extract from this is that we do have a large number of energy eigenstates participating in the dynamics. So assuming there's a lot of states contributing to the dynamics, trace of omega squared is going to be exponentially small. And then we're going to expect equilibration over the infinite time average to occur. We're going to expect our observables expectation value to be strongly concentrated around equilibrium. And so this is a proof of quantum equilibration. It is an infinite time statement, but it's an intuitive proof. It's a very cool proof. So I hope you got something out of it. I apologize for my bad handwriting. Unfortunately, I do have a writing tablet, but I'll probably need to upgrade it at some point if doing this becomes sort of the standard way that I make videos. But anyways, I hope you liked the video. If you did, feel free to like, subscribe, and leave a comment below. I will see you next time.